Hello. Okay. Yeah. So just for people who who wasn't here in the morning session, we will be having some hands-on sessions using the Jupyter Notebook. And to set up the notebook, you will need to send an arbitrary email to the address shown up here, emlp19-d2l at request-nb.mxnet.io. And then you will get a confirmation email, and then the notebook instance will be set up in about 10 minutes. Yeah, and we'll go through some of the examples and exercise on that in the afternoon. So just to give people some time to set up, we'll start the session in about 5 minutes. So in the afternoon session, we'll be focusing on BERT, which is a large-scale pre-trained language model, and we'll go through the fine-tuning process to develop a question, answering, or reading comprehension model. Okay, so here I'll just give a brief introduction to the BERT model. I'm sure most of you already heard about it, but let's just get an overview of it. Okay. Okay, let me try to fix the format. Okay, so the key idea behind word vectors is that we would like to get the word meaning by by its neighbors or its context. And then we can learn a vector representation of the word based on the distributional statistics of the word and its neighbors. So starting from word vectors, so here the distributional information we use to learn this vector representation is the word co-occurrence statistics. So basically, which neighboring words would the target word likely to co-occur with in big corpus. For example, in word2vec, our training objective is to predict the word based on its neighbors. So here, we would aggregate all the neighbors of the word within a fixed window, for example, the left and right 5 words, and then aggregate over the entire corpus. And in the end, we would get a one vector representation for each word type. But what are the potential problems here? So it's very likely that the word have multiple meanings, like bank as in financial bank, or bank as in bank related to rivers. So in order to solve that problems, recently people are started to using contextual word vectors. So compared to the non-contextual word vectors, here we have one representation for each word token or each word occurrence. So if the same word occurs in different contexts, we will give them a different representation. So in this case, the distributional information we're using to learn these vectors is language modeling. So we want to predict the probability of the specific word given its surrounding context. So compared to word vectors, we're using a fixed window around a particular word. Here you can imagine that we actually have an arbitrarily long context for each word in the contextual word vectors, because in language modeling, we don't have any limitations on the side of the context. Okay, so ELMO was the first successful model using contextual word embeddings, and then it significantly improves a bunch of natural language understanding tasks in the GLUE benchmark, such as sentiment classification, paraphrasing, natural language inference, and so on. And later, the BERT model from Google further improved that by using a better pre-training objective that we will cover in a minute, and larger data sets. Following BERT, we have RoBERT and AllBERT, which are different variations of BERT, and they further improved the performance. And also we see increasing number of papers focusing either analyzing BERT or fine-tuning BERT for various tasks. Okay, so what is the BERT model? Essentially, it is a big transformer encoder. So in the morning, during the machine translation session, we covered about the transformer architecture. So here, the BERT base model uses 12 transformer blocks, and it has over 100 million parameters. And the BERT large model uses even more, doubles the number of blocks, and it has over 300 million parameters. Okay, so now that we have this big transformer architecture, how do we learn this model? So BERT, to train BERT, we rely on this self-supervision objectives, which means we just need unlabeled corpus, and then we'll create training examples from that corpus. So the first pre-training task is masked language model. So compared to ELMO, which we use a bidirectional language model, where we predict one word based on its left context and right context. So here in BERT, the main change is that we have this masked language model where we predict word using both left and right context. So in this example, the input is deep learning is fun, and we would mask the word is, and then when we train BERT, we try to predict the masked word. So you can also think of this as a denoising autoencoder, where we add noise to the input sentence by masking some words, and then the model or BERT tries to reconstruct the original input by predicting the masked word. And the loss is the negative log likelihood of the masked word given all of its context. Yes?
Are the words complete, like are there complete words giving into the input? Was there...
Oh, yeah.
The P is missing and the G is missing, but it's just on the... You see there's not the deep, but the P is missing at the end.
Oh, right. Yes, so the format, because I adjust the aspect ratio of the slides, so it should be complete words in this slide. Yeah, but I also want to mention that in the BERT model, they didn't use word level tokenization. They used subword embedding, so it's a word piece. So it's likely that you have learn and then ing as separate tokens. But here for illustration, we just show complete words. Okay, so the second pre-training objective is next sentence prediction. So here, given a pair of sentences, BERT tries to predict whether the two sentences are adjacent or not. So again, this is the self-supervision objective. We just take a sequence of two sentences from any corpus. And to learn this model here, in the input, we have, let me quickly fix this. All right, so when we have two sentences in the input, we have this CLS, which is a special marker to aggregate the information in the two sentences. And the first sentence is NLP is fun, and then we have this separator, which is another special marker to separate the two sentences. And the second sentence is hello world. And then we need in order to predict this pair of sentences, we need one embedding to aggregate its information. So in BERT, we use this CLS symbol. So we take the embedding of the CLS, so we get a dense vector at the top there, and then given that, we would make a prediction, we make a binary prediction of whether the two sentences are adjacent or not. And in order to differentiate which sentence is the first, which is the next, BERT also has this segment embedding, basically either 0 or 1, to indicate which sentence the word is from. Okay, so this is the two pre-training objective people use to train this BERT model, very large corpus. So once we have this pre-trained BERT model, we can give it its sentences, and then it will produce embeddings produce contextual word embeddings at each position in the sentence. So then we can use this as the initialization and fine-tune the BERT model to adapt to any other downstream tasks. So in the fine-tuning stage, we use the pre-trained BERT model as initialization. And then we basically would like to add another classifier on top of the BERT model to make the task-specific prediction. So for different tasks, we have slightly different fine-tuning procedures. Like for single sentence classification, in the input, we have the movie is great. And then we would like to generate one output, either positive or negative. So then, as we mentioned, we aggregate information through this special CLS label so that we get one dense vector representation of the entire sentence. And then we can just have a linear classifier on top of that to predict the sentiment. And sentence pair classification is another type of task we're interested in. So here we can, so in this example, we have paraphrase classification. And in other examples, we can also have natural language inference. So here we're given two sentences, and we try to predict whether it is a paraphrase or not. So then the fine-tuning procedure is similar to the next sentence prediction task, where we have, again, we aggregate information through the CLS special label, and we have the separator separating the two sentences. And prediction is made through the dense vector from the CLS label. Right, so that's single sentence and sentence pair classification. And another very common NLP task is sequence labeling. So here we have the input sentence, such as Jim bought 3,000 shares of Amazon in 2006. And in the output, instead of generating a single label for the entire sentence, we want to have one label for each word. So in this case, we want to label Jim as person, Amazon as organization, and 2006 as time. So this is known as name entity recognition. In this case, we would actually use so instead of aggregating semantic information across the sentence, we would use the embedding at each word and then have a dense layer on top of that to make prediction at each word position. Okay, and also question answering is slightly different from either classification or sequence labeling. So in this case, we're given a document or description text, and we're also given a question. So in this example, the document is AMLC 2019 is held in Seattle, and then the question is, where is AMLC held? And in order to generate the answer, we will predict a span from the input. And we just take the span as the answer. So in this case, we will take Seattle as the answer. The model actually just predicting a starting index and an end index in the input document. Okay, so during fine-tuning, we use BERT to encode both the question, where is AMLC held, and also the document, AMLC 2019 is held in Seattle. And then for each word in the document, we will have two dense layers. One is used to predict the probability that this word is a starting index, and the other is used to predict the probability that the word is the end index. And then at decoding time, we would find the pair of starting and end index that has the highest probability. So that will define the span in the document, which is the answer we're going to output. And we will have a hands-on session on building the question answering model shortly. Okay, so in Gluon NLP, we provide many pre-trained BERT models. You can easily download the model by using this API, get model. So here we have this 12-layer BERT, which is the BERT-based model. And it's trained on the Wikipedia case corpus. But we also provide many other BERT models, using both BERT-based model and BERT large model, trained on either the original book corpus and Wikipedia dataset, or the scientific or text from the biology and scientific domains. Okay, and this is just results from the BERT models training Google NLP versus Google. So in most cases, we can reproduce the results, and in some cases, we're slightly better than the models trained by Google. So in the next session, we're going to look at how we can fine-tune the BERT model for question answering.
All right, so just for the people, in case somebody hasn't seen this in the morning session, so we provide these notebook instances. There was an email address that you could have sent an email to. You get a link to these notebook instances. Then you can click on the NLP 19D12 folder, and for this session we then go to the 0-free BERT folder and click on this IPyNB. If anybody needs the email address still, then just raise your hand and I can quickly show it. But okay, so please send an email to that address, and in a few minutes you will get a link back, and then you can directly follow through the hands-on practice. All right. Okay, so in fact for this session we want to tackle a, let's say, more complex task than the normal QA. So we want to do low resource QA. So we will just train only on a smaller subset and see how well that still works. And also it will allow us to train faster. So if you have the notebook, you can just maybe click the Run All button, because the training will still take around 10 minutes. So if you click that button now, then it will already start, and you will see the results earlier than if you wait until I get to that point in the presentation. So let's just import all the basics that we need. So maybe let's take first a look at the QA dataset. So here we use the squad dataset. So we can just use the GNU NLP nlp.data.squad API to get that dataset. And we will here now get both the training and the development part. So let's look at how each sample in the dataset looks like. So the first element would be just an index. So that just refers to the position of that sample. So this is the first sample. We start with 0. And then the last sample would have the number equal to the number of samples. We have some question ID, we have a question, and then we have some context here, out of which we want to find the answer, where this one would be the answer, and that is the position of the answer in our context. So now for low resource, we want to downsample this dataset. So how can we do that with our GNU APIs? So we have a sampler API. So if we take our dataset and we call .sample, and we provide a sampler, then we will get a downsampled dataset. So the sampler essentially needs to implement the length and iter function, and it will just provide the indices of the original dataset that we want to sample. So in this case, we just downsample based on some ratio. So let's say we want to sample maybe 10% of the dataset. We provide the length and the 10%, and then we will just randomly pick 10% of the tokens. So we just arrange the numbers from 1 to the end, we shuffle them, and we select the first 10%. So if we do that, then we get the following result, right? So we get 10% of our data set. So you already saw that in the slides before. Then let's use the GNU NLP model API to get our pre-trained BERT model. So we will just fine-tune it here on the QA task. In this case, we will choose the open web text, book corpus, wiki, and uncased datasets. So essentially, that's just a model that is trained on a concatenation of all these datasets, and it performs quite good because it was trained on a lot of data. So For the purpose of fine-tuning for QA, we don't need these like classifier, decoder, and pooler parts of the pre-trained model, so we will just set these to false and they will not be returned. We not only get the model, but we also get the vocabulary, so we can take a look at the vocabulary. So it has 30,000 tokens approximately. These are actually subword tokens. You will see in a moment how that looks like. And then also has these special tokens, classification token, separator token, mask, and padding token. So usually when we input now the question and the answer, we will put them both together as one input, but we will separate them by the separator token. So we can also define or obtain a tokenizer for the BERT model. So this tokenizer here from the GLUE NLP API, it just follows the same standard preprocessing or tokenization steps as is typically done for the BERT model. We provide the vocabulary, and we specify in this case that we want to use only lowercase, that we want to lowercase all our inputs. And then if we take the following sentence, you will see it will split up some of the words. So for example here, suspending is actually split up into 2 tokens, where these 2 symbols here indicate that it is to be appended to the previous token to get the full word, if you would like to detokenize it, but the model will see them as independent tokens. So now that we have our dataset tokenized, we need to pre-process it for our QA task. So we also provide an API for that in the GLUE NLP package. Essentially, here's an overview of what it does. So there's a few steps involved. So maybe you can quickly read through it. So essentially, we tokenize the text, and we take care that if the context is too long, that we just like take different windows out of that context, and for each of them we can later then perform the inference or the training with our model. So consider the BERT is trained only or is pre-trained only with the context length or with the input length of maybe 500 tokens, but you get a context that has 1,000 tokens, and you can't feed that in during the fine-tuning, so you need to split up your fine-tuning sample into 2 or 3. So that is also done here in this pre-processing logic. We will insert these classification and separation tokens and generate the correct start and end positions for the answers as well as the valid length input. So let's see how that looks like. So we can just instantiate this class with our tokenizer that we got before. So for the purpose of this tutorial, we will just flatten our return data set. So essentially, I told you if there is some input sample that is too long so that it can't be like fit into the BERT model at once, we need to split it and use windows on top of that. So the return of this Scott transform would be each item would be a list, and that list would be of length 1 if we didn't have to split up the sample, but it could be potentially longer if you would have to apply this windowing trick. But for now, we just flatten that, so we get just a list of samples. So we apply that to our transformed data set. And then we have to look into batchifying our inputs. So we use this batchify logic that we talked about in the morning. So in this case, the first element of our data set was the example IDs. So we just stacked them together in the batch. Then the second ones, these were like the second and third, these were texts. So we have to pad them to the same length. And then for the remaining 4, we can also just stack them. These are just individual numbers. So once we have defined our batchify function, we can pass that to the data loader and specify the batch size that we would like to have. And we can actually use multiprocessing here to parallelize the preprocessing step. And we can specify if we want to shuffle or not shuffle the data set. So now let's see how can we define the model that we want to fine-tune, right? So previously we got the pre-trained model. So we need to adapt that for the QA task. Essentially, we can define this BERT for QA model here. So all we do is we just take the BERT encoder as a parameter in our constructor, and then we also initialize a small dense layer with 2 output units, which we use to classify if a certain token is the beginning or end of our answer. In the forward function of this model, we compute the output of our pre-trained model and then return the output of our newly initialized span classifier. So when we instantiate this network, we just have to initialize the weights of that span classifier because the other weights are pre-trained and we actually don't want to reinitialize them. We can, in this case, select a subset of the parameters for which we don't want to perform weight decay. And we can collect all the parameters that we want to learn with the following call. So here the grad rec equals to null would mean that we don't want to update the gradient of that parameter. Then let's look into how we can train this model. So essentially we can use again the estimator API that we talked about in this morning. So we will have to extend the estimator again because this example is a bit more complex. So we define a few hyperparameters like the number of epochs that we want, some warm-up ratio, number of training steps, and number of warm-up steps. So in this case, we will make use of a learning rate scheduler, which will be invoked by the estimator using its handler API. So for this session, I will just import that from an utils files, but actually in the following session, we will also look into how we can implement such a handler ourselves. But for now, you can, or you will have to trust us that it does something meaningful. Or you can look at the utils file and see how it's implemented. So essentially, this learning rate handler, it will get the trainer, it will get the number of warm-up steps that it should take, the number of total steps taken during training, and the learning rate. So we want to achieve, or we want to like warm up to the learning rate provided here after number of warm-up step batches, and afterwards decrease our learning rate again until the number of train steps is reached, which would be the end of training. Then we provide, or we compute, we create the metrics, and finally we pass, well, let's skip that part for now. We pass all of that to the QA estimator. So the QA estimator would be our adaptation of the normal estimator, specifically for the QA task. So let's look at that. So for the QA task, we have to override the fit batch function here to properly handle the training batch. So remember, if we don't override that, we expect the training batch to only have two elements, which would be the input and the label. But here we have more elements. So specifically, we need to handle the data, the token types, the valid length, the start label, and end label. So for the fit batch function now, we override it, and then we can provide an implementation that handles the outputs from our data loader. So we just pass them forward for our network and perform the prediction, and then pass them through the loss. So the output now of our network here, you remember we had this dense classifier with two output units. So the first of that predicts is the current token beginning of an answer. The second of that predicts is the current token the end of some answer span. So here we treat them independently. So therefore we transpose these two last dimensions here and then pass it through the loss. So the loss would be the softmax cross entropy loss. And finally we just take one step with our trainer, right? So, and you remember in the previous slide I defined the learning rate handler. So that handler would be invoked before the fit batch function is called on a batch and would adapt the learning rate according to its policy. So that the trainer here always has the right learning rate to some degree. So the evaluate batch function is adapted in a similar fashion. And then we can just fit the model. So in this case, we just train it for 2 epochs on this 10% of the data set. And it takes around 10 minutes, and we get the results here. But let's see how it works in practice. I mean, we can now evaluate it, and we can try to see how it performs with some question and answer that we provide here as an input. So for that, we define a predict function which has some tricks. Let's just skip it for now and look at how it works. So we can call this predict function with our network and provide it with our development set. And now we will just look maybe only at the first sample from that development data set. And in this case, we had the question as follows. So it was about some NFL team in the Super Bowl. And we get the prediction here that Denver Bronzos. You know, we can read the context, and you can decide is that actually correct or not. Right, so we have it here in the second sentence, so I think that seems correct. Right, so we can also get the scores on the overall data set. So that was a quick run through how we can fine-tune BERT for the QA task. So for the hands-on part of this session, actually, I would like you to try, can we actually reduce the data set even further, and how do the results change? I mean, how small can we make the data set and still get good results with this model? So that's one task that you can choose. There's also another task that you may choose. So there's a concurrent share task here at the conference. So the MRQA task essentially is about out-of-domain data. So they provide their own data set which follows this quad format. So you could also adapt the data loading part of this notebook and try the model on the data provided by that share task. So yeah, maybe let's first look at the first task. So essentially what you would have to do is you would have to define your sampler here to subsample the dataset in a different fashion compared to what was done earlier in this notebook. So remember, earlier in this notebook we just sampled 10% of the dataset. So as a very easy example, you could just take the same sampler and just set it to 1% of the dataset or 5% and see if it still works. Or you could try something more advanced and try to select which samples you actually want to keep. So maybe you could consider, I only want to keep all the short sentences, like all the short context spans, and train only on them, or I only want to keep the long ones. Or maybe, given that you have already trained the model before now in this session, you can look at which answers does that model get wrong, and maybe you only take these hard ones, or maybe you only take the easy ones. So there's many options. So you just have to implement this sampler here, and then try it out. So time for exercise. Yeah, so if you have any questions, please raise your hand and we will be walking around and helping you. Right, so as you're reusing the notebook instance from this morning, you probably didn't shut down the notebook, the machine translation notebook that you used before the lunch break. So the GPU memory is still occupied by that model. So if you now just go ahead and run the QA model, it will fail due to some out-of-memory error. So I will show you how you can shut down the notebook from the morning so that the current notebook will run. So if you go back to this overview site, there is a tab called running here. And for me now it will only list the QA notebook, but for you most likely there will be another few notebooks shown, and you just click shut down for each of them that you don't want to use, so for all besides the QA notebook. And then you go back to the QA notebook, and what you have to do then is you will have to click on kernel and click the restart and run all button, and then it will just restart the Python interpreter and rerun everything. And then the GPU out-of-memory error should disappear. Okay, did anybody obtain already some results on the exercise? So one thing to watch out for is that if you now define your new subsampling logic, for example, in the exercise number 1, and you just fit the model on that data set, then we still use the model that is trained before. So we just kind of continue training it further. So if we really want to compare training on the small data set to training on the large data set, then we will have to go back and actually reinitialize the model. So there's a few steps involved there. So the first would be that we go to the part where we use this NLP.model.getModel API to get the pre-trained model. Then we can just go to where this pre-trained model is used, which is where the BERT4 QA model is initialized. So we also run this part again and collect the parameters again and just redefine all of these going down here, all these cells. Like, for example, the trainer needs to be run again because we now have a new set of parameters, right? So we will just redefine this trainer. And we will redefine again also the estimator. And then you can go down to where you have defined your own random sampler now and train the model there with the estimator. So if you do want to train a new model, right? So if you just want to continue training, then you don't have to take these steps. So that depends on which task you choose. So would anybody like to share their approach to subsampling? What have you tried? So one very naive, try is to just use an even smaller data set. So for the demonstration purpose for this exercise, I took again the same random downsampler and I changed it to just 1% of the data. And if you look now at the result after evaluation, you find that the model loss is much higher, right? So now it's here around 1.7 almost, and if we go back to the previous result, then it was around 1.2. So we find there's a large difference in the model loss, and we can maybe wait for the evaluation on the actual sentence to run so that we can also print them. But so, the challenge here is that if you maybe define some smarter subsampling scheme, you may be able to still get good results even though you train on smaller data. So here your creativity is essentially called upon. Okay, so if you look at the answers provided by this naive, like subsampling, like taking even less data for the first sample, so actually we find we still get the same response from that model, but its confidence decreased dramatically. So we have actually here only 24.3%, whereas previously we had like kind of a very clear response from that model where it says, okay, 95.57% for that prediction. So we may be able to look at some other samples. Okay, so if we, for example, take a look at the 10th sample of the data set, and we find that actually the response of these both models is still the same. And in this case, there is not that much difference in the confidence. So we can, go on and explore other parts. Okay, so here actually we do get some very different or like partially different response. So if we look at this question, who were special guests for the Super Bowl halftime show? Our model trained on 10% of the data says Beyoncé and Bruno Mars. And we can read the context. CBS broadcast Super Bowl 50 in the US. Well, anyways, you can read it. So we find here these two are listed as the special guests who headlined the Super Bowl halftime shows. So that is the correct answer. But then if we look at the output of the model trained on just 1% of the data, we find it still identifies here. The correct answer is still contained in the output of that model, but actually it also selects some more content. So here the answer would be, or the prediction is, Coldplay with special guest performers, Beyoncé and Bruno Mars, where Coldplay wouldn't be the special guest performer. And also the confidence of the model is much lower. So did anyone finish training their downsampled model? Okay, so maybe also let's talk about the second exercise. So for the second exercise, the idea is that we want to evaluate on another data set. So in this case, it would be an out-of-domain data set, so it would be different to the domain that we have trained on. And we would take a data set here from this share task. So if you go to the GitHub page of that shared task, it's just github.com/mrqa and then /mrqa share task 2019. You will find that they link a number of data sets in their README. So some of them would be out-of-domain data sets. So all of these data sets follow the same format as the squad data set that we use now during this session. So in fact, it's relatively straightforward to just adapt the data pipeline to these new data sets. Essentially, you only have to swap out the data set definition, right? So I will walk you through how you can do that. So if we go to the Gluon NLP GitHub repository, then we have here this source Gluon NLP folder, which is the main implementation of the Gluon NLP package. And inside there are different modules. So one of them is a data module. There's also the embedding, initializer, loss, metric, model, optimizer, utils, and vocabulary modules, of which most of you have used most of them today. So let's look at the data one. So in fact, there's some implementation for many different tasks here, and one of them would be question answering. And you would find that there is the squad data set here that we have used just previously in the notebook. So if I go back to the notebook, then in the very beginning we use this nlp.data.squad, and we specified here the train segment and the version, and we got the original data set, right? So this is the implementation here. And if we now want to, load another data set of the same format, and essentially we can take a look at this implementation and see how we need to adapt it. So what you will find is that in the initializer function, or in the constructor function of this data set, essentially we specify the different files that the data set is loaded from, together with the hashes. So for the train version 1.1, essentially it would be this zip file here, and it would have the following SHA1 hash. So if you were now to try loading a different data set, essentially, you could just subclass the squad class, and you would overwrite this self._data file in your constructor, and you would put the correct SHA1 sum here together with the correct name. And if you would like to load it, then you would also, change the name, of course. So this would be the location where the dataset should be stored. So it would be in your home directory or in the mxnet home directory, which is the .mxnet folder in your home directory. Datasets squad. And for the purpose of this session, it would actually be this datasets folder over here. So you see here, now there's a squad folder. In that squad folder, there are these zip files. So if you were to download now the dataset from the share task, so for example, we could take this bioasq and download the zip file and just calculate the hash sum and put it into the _data file, then you could directly load it and plug it into the data pipeline that we have defined in the notebook. So if you're interested to also try or work on the out-of-domain QA tasks, then that would be a good chance to get familiar with how to use the datasets. Okay, so in fact, this textbook QA dataset doesn't follow the same format as Squad, so we would have to adopt the dataset class to parse the JSON format correctly that they use. Okay, so starting from 3:30 until 4, there's a coffee break downstairs. So at this point, I think everybody who wants to get some coffee can do that. And after the coffee break, we will continue with a session on large-scale training. So how can we train models in a large scale? We will present some tricks for making computation more efficient, such as reduced precision training or quantization, for making inference more, take less resources. And then finally, we will also cover a deployment session, so how we can take a fine-tuned model and deploy that in some cloud service, so that you could then, for example, build a web application or a mobile application that queries the model that runs there, and the cloud will automatically take care to provision enough resources to run your model depending on how many queries there would be from your users. So it is kind of very easy to deploy, and you will see how that can be done with Glue and NLP, for example. Thank you.